All right, in this video, we're going to talk about half-life, which is technically covered on pages 13 and 14, but it's not as long as it sounds. It's just a little bit at the bottom of page 13, a little bit at the top of page 14. It's barely any notes, but then we're going to work a few problems that use this idea. So, this is kind of just a random added topic that relates to the fact that we have those first-order reaction equations. Radioactive decay is always first order, and that's chemistry, atoms breaking down into different atoms. But FYI, nuclear chemistry is not tested on the AP exam, but all that really means is you don't need to memorize the different types of decay and fission versus fusion. You might be given some examples of nuclear chemistry and told the first order reactions and expected to be able to do calculations like we've already done with that first order equation and or this half-life equation, because that's something that's special that we can do first order equations, is they have a predictable half-life that does not depend on their original concentration. So be ready for that. Don't get to a nuclear chemistry question and go, we never learned this, because it's probably not really about the nuclear chemistry. It's probably going to tell you it's first order, and that's all you need to know from that kind of question, other than some of those numbers. Now, what is half-life? Specifically, it's the time required for the concentration of a reactant to decrease to half of its initial value. So the time it takes to become half as much. That's the half-life. And we have this equation, T1/2 equals 0.693 divided by K, that only applies to first-order reaction half-lives. And you'll notice it doesn't depend on any concentrations. It's just this funny 0.693 number divided by the rate constant K. So if we think about this, a fast reaction, meaning something with a fast, short half-life, is going to have a small half-life, and that's also going to mean it has a large K value, because large K values will make our T half smaller. And conversely, if it's a slow reaction, that means it has a very large or long half-life. It takes a while for it to decrease its concentration, which means that would generally have a small K. And this matches what we've talked about already. If we ignore the half-life equation at all, fast reactions have big K. So those rate laws, rate equals K times our concentration. Bigger the K, bigger the rate. So this isn't anything new, and it's reinforced by this equation. Keep in mind, this is just first-order reactions. There are other half-life equations, but they get way more complicated, and AP will never test you or ask you about them. It has to be first-order if we're talking about half-lives. So you may be asked to calculate the half-life from K, or find and apply the half-life over a given amount of time. But anytime you see a question that mentions it's a first-order reaction, like this first example does, then your brain should be looking at that equation sheet and looking at that T1/2 equation. And so if we read through this question, it asks if 87.5% of an unknown element decomposes in a first-order reaction in 24 days, what is the half-life? So you actually don't need to use either of these equations. You could use that second equation, the integrated rate law, for this and plug in these percents as if they were your concentrations, but we don't have a K. So we couldn't solve for T, and that would also make our half-life equation hard. So you might sit here and go, but my equations are useless. But they've given us enough time to think through this. You can do this in mental math. What you need to kind of understand better and think through is the definition of a half-life. So if we start on day 0, before anything has even happened, we have 100% of our substance unreacted, and that means none of it has decomposed. After one half-life, the definition of half-life tells us that half of that unreacted stuff is going to react and decompose, which means after that first half-life, 50% of it is going to be unreacted and 50% of it is decomposed. So that doesn't match the numbers in our problem yet. So it's not one half-life that happened in those 24 days. So for another half-life, when that second half-life happens, 50% of the unreacted stuff reacts. And that was only 50% of our sample left at that point. So 50% of 50% means now all I've got left is 25% unreacted, and an extra 25% of my original sample is decomposed, giving me a total of 75% of my unknown element having decomposed. Still doesn't match our situation, so we know it isn't 2 half-lives that has happened. On that third half-life, half of our unreacted, half of that 25% that's remaining is going to react. That's 12.5% that's going to react more. So it leaves us with 12.5% unreacted. An additional 12.5% is decomposed, which when we add that to 75, gets to 87.5, which happens to match our problem situation exactly. So just by going through this process of understanding and kind of figuring out how many half-lives have happened, just with the definition of half-life, we know 3 half-lives have happened in those 24 days, which means that each of those half-lives has to be an 8-day half-life. So this is an example of a way that you can use the idea and the definition of half-life without actually having to plug in numbers. It didn't give us enough information to really plug everything into these equations. In our next example, though, we are going to have to do some math. As we read through this, this tells us a first order reaction, and we've got a K value, and then it just asks us for our half-life. So out of these two equations, we're going to be using our half-life equation. That's a simple way to get there. And all we've got to do, because all we need to plug in to find our half-life if we have K, is plug in that K value. I'm using E here for my scientific notation because that's how I'm going to plug it into the calculator. Just need to do 0.693 divided by that 2.2 times 10 to the negative fifth number. And when we do that, our unrounded answer is 7.8883 times 10 to the 16th. Because my given was just 2 sig figs, I round my answer to 2 sig figs. And pay attention to our units for half-life. It's going to be related to the units of time used in K, because that was inverse seconds. This is going to be regular old seconds for our final answer. Hopefully that's not bad. They do get a little bit more complicated. Like this next problem, example number 3, is about as complicated as they can get, but we just have to be systematic with how we approach it. This tells us that the composition of N2O5 is dissolved in this substance is this reaction. We actually don't need that reaction at all. What we need, as we keep reading, is that it's known to be a first order reaction. So at a specific temperature, the reaction was begun. We have an initial concentration. After reacting for 3 hours, we have a final concentration. It asks us what is the half-life of N2O5 expressed in minutes. So first thing we needed to notice was that first order reaction, then it's asking us for the half-life equation. So eventually we are going to want to use that half-life equation, but we need to know K before we can do that, and they didn't give us K. But luckily they gave us some initial and final concentrations and the amount of time, so we can actually plug those values in to this integrated rate law for our first order reactions and solve for K here and then plug that in. So like I said, it's as complicated as it gets where we have to use both of our equations, but it's really not that bad. So plugging this in, natural log of AT, that's the concentration at a specific time. So that's the 1.21 times 10 to the negative 3, minus the natural log of our original concentration, which was 1. That's equal to negative K times our time. And because they wanted us to express our time in minutes, then I need to turn the 3 hours that they gave me into minutes. So 60 minutes in every hour, so I multiplied 3 times 60 and got that 180 there. Now if we start simplifying this down and put those logs, and both of those logs and the subtraction into my calculator, that left side of the equation turns into negative 6.72, which is equal to negative 180K. I divide by negative 180 on both sides, and I get 0.037333 repeating. I did have 3 sig figs on both sides there when I was dividing, so our final answer should be 0.0373. And that's going to be inverse minutes. But remember, this isn't our final answer. This is inverse minutes because our units for K are always 1 over time for our first order reactions, but we need to use this to solve for our time, and that way our time will be units in a minute. But it's not too hard to do this. This is now just like the last problem. I'm looking for my half-life. I've got my K value. I'm just going to plug that in and then get an unrounded answer, which I'm going to round to 3 sig figs, 18.6, and that would of course be in minutes because I made sure to turn my original time into minutes, which meant my K was inverse minutes, which means my T half is in minutes. Just need to keep that time consistent throughout. Don't try and change these other values into hours to make those match. Get things in minutes. So hopefully that's not too bad. And like I said, that's the most complicated type of radioactive decay or half-life problem that we can work, where we have to combine both of our equations. So one last problem here, and this is asking us, I see it's a first order change of cyclopropane into propylene. We've got a rate constant, so we have our K value, we have an initial concentration, and we are looking for the concentration at a specific time, at 24 hours after the reaction begins. So this is multiple numbers that we're going to be plugging in, so we are going to be using that integrated rate law version of our first order reaction, and it is asking about the concentration at 24 hours, but if we notice that our rate constant, our K, is in inverse seconds, the time that we plug in as T is going to have to be in seconds to match that. So as we start plugging things in, we're going to be solving for that AT value. So the natural log of whatever that value is minus the natural log of that original concentration is equal to our K value times 86400, which is our 24 hours turned into seconds. Just times 60 to turn it into minutes, times 60 to turn it into seconds. Simplifying this up a little bit, combining our numbers on the right side of the equation and taking my natural log in my calculator, that simplifies down to natural log of x plus 4.61 equals negative 0.100. If I then subtract 4.61 from each side, I get natural log of x equals negative 4.71. To solve for x, remember, when I natural log of the thing that I'm looking for, in order to undo that natural log, I have to raise it e to that power. So I'm doing e to the ln x, which is going to turn into x, is equal to e to the negative 4.71. So x is equal to e to the negative 4.71. When I plug that into my calculator, x is equal to 0.0900407, which rounds down to 3 sig figs is just 0.00900. If you feel like putting that in scientific notation, I completely understand, but it's the same value either way. And then, of course, we're looking for concentration here, which means our units are going to be molarity. So, lots of different types of questions we can ask depending on what types of information they give you with that half-life. But just when they say half-life or say it's first order, you should be looking at those two equations and deciding which or both do we need to solve that problem.